Hi and welcome to this tutorial on how to analyze simple shear data. And I'm going to talk about 5 common mistakes that people make when they're trying to analyze or use shear data for material model calibration. Really, simple shear is a good test, but it's not so easy to analyze. So why do we even do simple shear tests? Well, in many cases, it's useful to have experimental data for different loading modes. We can do uniaxial tension, we can do compression. But shear is very tempting to do. It's easy to perform the experiments, and therefore people like to do them. But it's very important that you analyze them properly, and that's really what I want to talk about here today. First, I want to remind you that if you haven't checked out my other article on simple shear, I will mention that here that I wrote an article about large strain behavior in simple shear a few months ago. It's under polymerfem.com/simple shear. And there's some information there that I'm not going to talk about in this video. So take a look at that one if you haven't already. So let's talk about simple shear. So simple shear is very easy to describe. We may have a cube here. It's a block. In my example, it's 10 by 10 by 10 in side length. And then I'm shearing the top surface to the right, in this case by a distance of 10. And the question here really is, what is the strain in the specimen once I move the top surface to the right a distance of 10? Is the strain 1? Is it something else? What are the problems here? And I purposely wrote this problem statement in a little bit of complicated way. There are some issues with it, and that's what we will talk about here. So how do we do this? Well, you can analyze this very easily using a finite element program, Abacus or ANSYS or anything else that you have available for you. In my example, I'm going to use Abacus, as you can see here. So the boundary conditions that I'm applying are pretty straightforward, but it's worth talking about. The bottom surface cannot move upwards, and it cannot move in the X direction. The back surface I'm constraining so it can move in the Z direction. The top surface cannot move up and down, but I'm prescribing the horizontal displacement of the top, and I'm moving it a distance of 10. So I'm moving it as far to the right as it's tall. And there are other ways to specify boundary conditions, as I will talk about later, but this is a very common and easy to understand set of boundary conditions for simple shear. So if I run this simulation and I plot contours of the nominal strain 1, 2, so that would be the traditional shear strain. I get a single element here that I'm deforming, and the strain value according to Abacus is 0.894. And that's not 1. So 1 is, of course, the gamma value, which is the distance that I shear divided by the height of the specimen. So clearly, we need to first realize that gamma is not really a valid shear strain of any kind. It's a convenient way to describe the amount of shear. It's dimensionless, but it's not the engineering strain. It's not the nominal strain. It's not the true strain either. So as I will talk about in a few minutes, I will show you where does 0.894 come from. And this is big consequences, of course, if you get data. Of course, most test labs or the people that you work with, they typically report gamma, thinking that it's a good shear strain value, and it really isn't. So how about Truestrain? Well, Truestrain is very easy to plot in Abacus too. So that's LE12. I get a value of 0.860. So we switch back to the normal strain, 8.9. Truestrain is 8.6. They're again different, but they're not 1. We got to understand, of course, where does these numbers come from, and how can we analyze these properly. So here is a graph that I created. On the x-axis, it's gamma, it's delta L over L, and the y-axis, some kind of strain measure, shear strain measure, that is. The true strain, LE12, is the red one. The nominal strain, NE12, is blue, and the dashed line here is just gamma is gamma, so assuming that gamma is a strain measure. And we'll see that at really small strains, at small gamma values, indeed the engineering strain, the true strain, and gamma all are very similar. And that's why people are used to this. But at finite strains, if you have strains that are relatively large in shear, these three measures are not the same, and you shouldn't think they are the same. And that's important to think about. You can't get away with gamma typically if the strains are finite. So I would certainly recommend that you convert gamma to the engineering shear strain. So how would you do that? Well, it's very easy to go through. It's given on the blog post that I talked about a minute ago. And the final equation is here, that epsilon 1, 2, this is engineering shear strain, is equal to gamma divided by square root of 1 plus gamma squared divided by 4. And if you plug in gamma equal to 1 in a math calculator, for example, Julia, and then you type in this equation, you get that the engineering shear strain according to this equation is 0.894. And if we switch back to our Abacus results, 0.894, it's the same thing. So that's how Abacus does it. That is the engineering strain, the nominal strain. And you can calculate it from the gamma value in this particular way. How about the Truestrain? Well, the Truestrain is different than the engineering strain. And you can see kind of the calculation there. And I will do this live for you too, because it's kind of easy to do. It's interesting. So I opened a Julia window. Julia is my current favorite math calculator. It's free. You can find out about it. You can download it. It actually works really well. So the problem with Truestrain is that there is no simple closed form solution that is worth deriving. So therefore, I was going to calculate it. So the deformation gradient is where we start. It's for simple shear. In our case, it will be like this. So here's our deformation gradient. The left stretch tensor is F times transpose F. The V tensor is equal to square root of B. And the tensorial strain tensor is given by the logarithm of the natural logarithm of V. So that's the tensorial strain. The shear strain, the engineering shear strain, which is what the strain values that Abacus and ANSYS compute have twice the shear values what you get for this equation. So strain 1, 2 would equal to 2 times strain, and then it's the 1, 2 component here. So like that, 0.86 is the true strain when you have a gamma value of 1. And you can calculate it just like I did here. So let's go back and take a look if we know what we got. Yeah, 0.8608. That agrees with the little calculation that I performed. You can see it summarized here. So that's easy to calculate with a math calculator if you like. You don't typically need to do it, but it's good to know how you would do it if you need to. Another complication with simple shear is related to the out of plane. So that is the direction C here, the 3 direction. If you have the boundary conditions that I introduced earlier, you will have a deformation in the out of plane direction. And we can see that in Abacus. We can just plot NE33 or LE33. It's not going to be 0. So if you want to have it 0, if you think that's better, you would have to prescribe that the front surface of your specimen cannot move in the 3 directions. So that's perfectly valid to do. It's up to you, depending on how the experiment was done, to decide if that's something that's better for you or worse for you. So what's typically the best way though, right? Well, think about experiments. So if you do a simple shear experiments, often people use a single lap shear. I typically recommend a double lap shear. It's self-centering. In that case, you basically take your specimen in darker gray here, and you glue it to these metal pieces. And then you shear these the way it's indicated by arrows here. If you do that, the material is not really allowed to expand in the out of plane direction. So therefore, the displacement in that direction is 0. The strain 3,3 should be 0 in most experiments if you do it in this particular way. And if you want to use experimental data from shear in MCalibration, you want to analyze the data, you want to calibrate the material model. Well, MCalibration has 2 kinds of simple shear. And this is something that is worth be aware of course, if you have shear data. One is just called simple shear, and there are different directions to it. And the other one is simple shear fixed. The fixed version of it doesn't allow the material to have a displacement in the 3 direction. But the traditional simple shear one allows a displacement in the 3 direction. It doesn't change the shear strain 1-2, but it changes the pressure and it changes the response in the 3 direction. So I would certainly think carefully about which of these you pick when you work with MCalibration with simple shear data that you have generated or someone generated for you. Another issue with simple shear is that it really isn't so simple. So if you do a finite element simulation, but you don't have a single element, you divide your specimen in many elements. In this case, I did 1000 C3D8H hybrid elements, and I deformed it to gamma equal to 1. And in this case, we'll see that it looks kind of weird, right? It's like it's not homogeneous. The max stress divided or related to the minimum stress are totally different. It's not a homogeneous stress state. And this is something that's important to remember. In a uniaxial tension test or a compression test, as long as you don't have friction, you have a homogeneous stress state. But in simple shear, you don't really have a homogeneous stress state. You can make it homogeneous by having one element, but that's cheating. In the real experiments, you will have edges of your specimen that don't have the simple shear state in it. And that's a problematic situation, of course. So one way to improve that is to have specimens that are relatively wide. So here's a figure that shows the stress. So how do you find stress? Well, the stress is not homogeneous after all. Well, I define stress by the force that was applied on the top surface divided by the area of the top surface. So that's the traditional engineering stress definition. So that's stress. And then I compare that to the finite element predictions of different specimen dimensions and shapes, right? And I'll see that if I have a specimen that's equally tall to its in-plane directions or dimensions, so h over b equal to 1, I get an error in the stress if I use this definition. That's almost 20%. Really not good at all. I would be very careful using experimental data obtained in that way if I don't take a little more care when I analyze the data. But if I have specimens that are 5 times wider than they're tall, so they're very wide and not too tall, then this edge effect becomes much smaller. The error is less than 3% or so. So my rule of thumb is, well, I try to have my specimens quite wide, hopefully 5 times wider than their height. In this case, the influence of this inhomogeneous stress state at the edges becomes less important, and I get good data in the end of the calibration that I'm working with. So to summarize, the 5 common issues that I see people work with or run into when you're working with simple shear. The first one is that engineering strain is not the same as gamma. You really should be very careful about that. Use the equations that I showed earlier in this presentation. There are different kinds of simple shear in MCalibration: simple shear and simple shear fixed. Most of the time, you should use the fixed version. And we talked about converting it. If you have really, really small gamma values, you can just assume it's the strain and you'll be fine. But at any other time, you should convert it to proper strain, just like we talked about. And finally, the other one here is that simple shear is really not a clean test. It's kind of a complicated test in detail. The edges are different than the interior, and that can cause kind of problems. To experimentally improve it, use wide specimens. That helps with accuracy. And finally, if you are stuck with specimens that are not that wide and you want to still use the data, there's nothing really wrong with the data. You just have to be careful when you analyze it. And the way you do that is to use an inverse material model calibration approach. You would actually create a finite element model of your specimen, particularly the geometry that you analyzed. And then you have MCalibration drive that calibration in an inverse way. So you simulate, using the FE solver, the deformation state, and that will allow you to fully understand what's going on. But it's a little cumbersome, obviously, not as quick and easy as if you don't have to do that. That's why I recommend wider specimens if you can get away with that. So that's it. Hope you found this useful. Let me know if you have any questions. You can always head over to polymerfem.com if you want to learn more about it, or if you want to ask your questions there. Thank you. Bye.